All right, hello everyone. So I'm not going to take the time to walk through every single problem from the practice for this weekend around particle motion, because some of them are a little self-explanatory when it comes to the answer document. So I'm not going to necessarily walk through all of those. If you have questions about those, do reach out and I'm happy to meet one-on-one with you to answer questions, or during office hours we can talk about them. I do want you to understand them, but instead of spending the time on those, I want to spend the time on the more challenging problems from this weekend's homework, okay? So let's actually start on the problem that is BC2 Part 1, Part D, and it says if x of q is 6, if x of q of 6 is 105, there is a value k such that x sub q of k equals v sub q of k equals 0. And for 10 to c, the graph of v sub q of t is linear. Let's find c. So this is a very challenging question. It's definitely harder than what you would typically find on a free response question, but it's a good thinking question, so I want us to be able to process through this one. What I might actually do at first is just write down some notes for myself. For example, I know that x sub q of 6 is 105. And then we're also told a few things. We're told there is a value such that this equation is true. So x sub q of k equals v sub q of k equals 0. So I'm actually just going to kind of stop there. Let me just like write out what each of these things mean. X sub q of k. X sub q of k. X sub q of k. Well, how would I figure out x sub q of k? Well, I know I'm interested in some value of t that will go in here that's bigger than 10. So if I'm really interested in measuring x, the position stuff, bigger than 10, I can just say that x sub q of k, whatever k is going to be x sub q of 10 plus the integral from 10 until k, right? 10 till k. 10 till k of v sub q of t, right? dt. Now, this would give me whatever x sub q of k is. And so I have to then go, well, okay, this is x sub q of k. I know based off this equation up here that's going to be equal to 0 or equals v of k, so I'm not going to worry about that stuff yet. Let me just keep working on figuring out whatever this is. Well, that means I do need to know x sub q of 10. So let me figure that out first. X sub q of 10. X sub q of 10. How do I figure that out? That's a position. So I'm going to kind of need actually a similar setup over here. The position at 10, do I know any starting position? I do. I know x sub q of 6. So x sub q of 6, I do know. And if I add on to that the integral from 6 to 10 of v sub q of t, my q's are getting a little funky, I'm sorry. This should give me x sub q of 10. Right, so x sub q of 6 I knew was 105. 105 plus the integral from 6 to 10 of v sub q of t. What's v sub q of t? V sub q of t is the graph of g here. So that means I need the integral from 6 to 10, right? The integral from 6 to 10. 6 to 10. That's all below the x-axis. It's a 2 by 3 triangle, so that'll be an area of 3, but the signed area, oh, actually, sorry, my scale is important for this one. My scale down here is actually going by tens. So it's 2 by 30. So that's actually an area of 30 in there. Signed would be negative 30. This is 2 by 20. So that's an area of 20. Signed area of negative 20. And so if I then subtract, so that'd be plus negative 30 plus, so minus 20 would give me an x sub q of 10 position of 55, right? So let's just keep filling in what we know. I basically based off of that I need to know these things in here to do something. So I'm just trying to find x sub q of k, which I wrote out this way, knowing that k, we're interested in place beyond 10. I now know what x sub q of 10 is. So that means this is going to be 55 plus the integral from 10 to k of v sub q of t dt, right? I now know that. So here's what we got to start thinking. Okay, this integral from 10 to k of v sub q of t dt, that may be hard to get at the start here, but what do I know? What do I know? I know that this thing here is equal to x sub q of k, right? That's what I'm kind of working on here. But I know that in the end, that's going to be equal to 0. It's going to be equal to 0. Right? So what does this tell me? This tells me then, if I want to solve for this integral, what is the value of this integral? This integral, 10 to k of v sub q of t dt is going to be equal to negative 55, right? Negative 55. You kind of subtract 55 over there. That's what that integral value is equal to, right? That's what that integral value is equal to. Okay. So let's do a little bit of thinking here now. This is where we got to do some puzzling. If we think, okay, well, what do I know about v sub q? Because this integral would be the area, right? Signed area of v sub q from 10 to k. I am told that the graph of v sub q is linear. So if we kind of think about this, and this is the graph you see on the answer key. Ooh, wow, I got it. It's an ugly looking line. But this, if I sort of take what I know about v sub q, what do I know about v sub q? I know that v sub q of 10, the starting place of that, is negative 20. So starting at 10, I know my v sub q graph has a value of negative 20, right? And then I'm told that the v sub q graph t is linear up until c. So c is going to be some t value out here. I don't know what it is. It's way out there, right? And it's linear up until that spot. Imagine that's linear. So if I want the integral up until that spot, and in this case, we're now realizing that k and c actually have to be the same thing to make this work, right? K and C are really the same value. I actually think that that's a mistake in their wording here, that they should have clarified that K and C are really referring to the same value here. We kind of got to make that assumption to even make this work. So to make the integral from 10 to K equal negative 55, I need to figure out then, okay, well, what does this C need to be that would make this whole triangle area negative, or 55, right? So what's the base of this triangle? The base of this triangle would be c minus 10. The height of this triangle would be 20. So what I really want is I want half of 20, the height triangle times the base, which is c minus 10, to equal negative 55. Because if this area, the integral from 10 to c, which is that k up there, equals negative 55, everything else will fall into place, right? My position will be 0. That would mean at that c value, the velocity would be 0 also because it's touching the x-axis. Everything will work. So as I crunch this, that'll be 10. I can divide 10 to this side. That'll be c minus 10 equals negative 5.5. Because I multiplied that half times 20, that'll be 10. Divide 10 over there. I can now add 10, so I get c equals. Oh wait, actually, sorry, I want the area to be positive 55. I'm not going to worry about the signs right now. I'm just trying to find the actual area here. I apologize. So that'll be half times 20 is 10. Divided over there would be 5.5. I'm going to add 10. So that'll give me 15.5 as my value of C. All right. Cool. Another way you could have done this is if you could have called this depth negative 20, and that would be negative 55, and it all would have come out the same. So this problem, I do have a little bit of trouble with the wording of it. This is obviously not vetted and checked like the actual College Board exam questions are. This is stuff that that some of the guys putting together the videos online have helped out with, and it's a great question, but the wording does get a little vague. We do have to make this assumption here that C and K end up being the same thing to make this work. It's a safe assumption. It works that way, but I know it's a little uncomfortable to make that. All right. That's a challenging question. In these kind of situations, I would just like write down what you know, and they do like these ones that have these kind of dummy variables in there. Write down what you know x of q sub k is. Just write down. and then slowly return back to this and do the kind of problem solving that you can. Okay, let's take a look at E. It's actually a review of a topic we've not covered yet in our review. Okay, E says the conditions for the mean value theorem are met for V sub p of t on the interval 0 to 2. So V sub p of t, that's talking about this up here, right? My f of t graph. Okay. And t equals 1 satisfies the mean value theorem for this interval. Okay. So recall, the mean value theorem says that if you have an interval that's continuous and differentiable, if you find the slope across the interval, there's got to be a place, a time, where the derivative equals that slope. So basically they're saying that this is the time where the derivative f prime of t, so f prime of 1, equals the slope of that interval, f of 2 minus f of 0 over 2 minus 0. They're saying that this is the time where the derivative actually equals that slope over that interval. So what's our question? Find the second degree Taylor polynomial for x sub p of t, centered at t equals 1, and use it to approximate x sub p of 3. Interesting. Some reminders. Taylor polynomials. All right. This is the kind of question that you can expect on the exam this year. It has to do with the topics that are listed. It's a Taylor polynomial question, and we're using it to approximate a function. And that's really the only Taylor polynomial stuff that should be on the test this year is section 10.11, using Taylor polynomials to approximate functions. So, reminder, for a Taylor polynomial, we need this kind of setup, right? We need to figure out the function at the place where we're centering it times x minus a to the 0 plus the derivative at a times x minus a to the first power plus the second derivative. I guess I should use a different thing other than f because I'm using f as my general term, but I have f in my problem. Let me make this a little different. Let's call it h. H of a, h double prime of a, x minus a squared, and so on and so forth. Remember the sort of formula for each of our things. Oh, I missed something. Over 1 factorial over 2 factorial is over 0 factorial. Remember, our general formula is h k, whatever the kth derivative we are at of a, over k factorial x minus a to the k. All right, so we want to be able to write the second degree Taylor polynomial. We want to go up to this second power. So what things do we need? I always like to start with like my base stuff because the parts of your Taylor polynomial, the x minus a and the factorial, that stuff you just write that stuff down. You don't have to do any like calculating or work for each of those. The other parts we do, the h of a, h prime, h double prime. So we want to approximate, we want to write the Taylor polynomial x sub p of t centered at t equals 1. So that means we need x sub p of 1. Do we know x sub p of 1? Do we know x sub p of 1? We do. It is 5, so I'm just going to write it down. For my next term, I would need x. I'm trying to approximate, so h is my general function. I'm trying to approximate, write the Taylor polynomial for x sub p. So that means I need for my next coefficient up here, x sub p prime of 1. But what is x sub p prime of 1? That's the same thing, x sub p prime, that's the derivative of x. I know that the derivative of x sub p is v sub p, that's the velocity graph. This is really the derivative of x sub p, right? So that's really v sub p of 1. So what's v sub p of 1 up here? They say v sub p is f of t, so v sub p, this is my velocity graph, my derivative of x sub p graph, and it looks like it's 21. All right. Continuing on, what about my next derivative? That'd be x double prime sub p of 1. But here's where I go, okay, I don't really have a way of figuring out, I don't have a perfect way of figuring out the second derivative, but I am told, hey, wait, the mean value theorem works on the interval 0 to 2, right? And that t equals 1 satisfies that. That's going to be the place where the derivative of f, wait, the second derivative of x sub p, that is the derivative of f, right? Because f is kind of confusing, I know, but f, this graph, f, or this table f is v. So if I want to take the derivative of x sub p, I need to take the derivative of v sub p. Oh, but v sub p is up here. So if I do my mean value theorem from 0 to 2, I can find an approximation of the slope of v sub p at 1. And I know that at 1, that number I get from my slope will actually give me that first derivative of f, which is going to be the second derivative of x. That's actually going to give me the value that I want. So let me go ahead and do that. That's going to be equal to, let's see, I have this formula over here. F of 2 is 27.5 minus f of 0, which is 7.5, over 2 minus 0. Right? That's going to give me 10, right? And again, to recap, I know that I can do this because they tell me that on this interval, the mean value theorem works, and t equals 1 satisfies that conclusion for v sub p of t. So v sub p of t, or v prime sub p of t, is the same thing as f prime sub p, or f prime of t, which again is the second derivative of x, so I can do the second derivative thing that I want. All right, so I have all these things now. What do I do with it? This gives me all the information I need to actually write my second degree Taylor polynomial. So x sub p of t, using second degree Taylor polynomial, is going to be approximately, I start with this thing here, 5 over 0 factorial, but 0 factorial is 1, so I'm not going to even write it over, times x minus a. In my case over here, my a value I'm working on is a equals 1. Right, my Taylor polynomial is centered at 1, so it'll be x minus 1 to the 0. Oh, but that's just 1, so I'm just going to leave it at 5. Your first term is always a constant. Plus, my first derivative was 21 over 1 factorial, well, that's just 1, times x minus a is 1 to the first power. So there we go. Plus, my second derivative was 10, I found. Again, I got that from using the mean value theorem on, this is the first derivative table. This really is the first derivative. So I used the mean value theorem on the first derivative table to get the second derivative, and got that as 10. So it's 10 over 2 factorial. 2 factorial is 2 times 1, so it's just 2, times x minus 1 squared. All right, you can clean this up, but we can leave it like this. This is my second degree Taylor polynomial. I want to use it to approximate when t is 3. So I can say x sub p of 3 is going to be approximately 5 plus 21 times x minus 1 plus, I can, oh wait, I'm plugging in 3 though now, right? I'm plugging in 3 now, so it should be 21 times 3 minus 1, which will give me 2, plus 10 divided by 2 is 5, times 3 minus 1 is 2, squared, and whatever that gives me will give me the approximation. That's all I need. All right. So there's a good question. I want to look at one more just to give you some leg up in terms of how to approach some of these problems. Go ahead and delete this. The tricky part here is this mean value theorem thing. Remember that we wanted the second derivative of x. We have a table for v. Second derivative of x is the derivative of v, so I use my slope on v, which is f of t. And I knew that they said here that at t equals 1, that the slope will actually be the same thing as the derivative, and that's the derivative I wanted, so it was 10. Right. Let's take a look. A few quick comments about some other parts. So the first page up here, if you have questions on it, do let me know. But there weren't any sort of crazy challenging things. You might have to go back and look up some stuff. Do let me know if you have questions. One thing that makes part of this page a little difficult is we have to keep in mind the scale of things, because it says here a new situation during halftime intermission in the college football game. Popcorn is made and sold at concession stands. For 0 to 10, the rate of boxes of popcorn are modeled can be modeled by M of T. The rate that boxes are sold can be modeled by S of T, where M of T is F of T. So this is how they are made. And then the absolute value of this graph would give us how they're sold. So keep in mind, absolute value of this graph would be like flipping this. If you want to, you can even like sketch it up. Like we could say it's that graph. Or if you just want to work on making areas positive when you get there, that works too. All right. M and T are both measured in boxes per minute. At T equals 0, 120 boxes of popcorn are sold. This sounds like a rate in, rate out problem. That's definitely how you have to approach it. All right. We have seen those already this week. If it helps, do your little like diagram. We have, these are going to be my popcorns. Sorry, y'all. Sorry, Nina. My AP art skills. With my popcorn, I start off with 120 boxes of it. We have a rate at which they are made. M of T is a rate. This is an amount. And then we have a rate that they're sold. Right? This is a rate also. So we have a rate in, rate out. If it helps, draw this little diagram. Find S sub prime of 1. S sub prime of 1. Sorry, S sub prime, S prime of 1. Using correct units to interpret the meaning of that in the context of the problem. Here's what makes this a little difficult, right? S prime of 1. S prime, what is that? S is the absolute value of G. I can come up to my G graph. Absolute value, it's already positive, so I don't need to worry about that. But S prime of 1 would be the slope right here along this line. Don't be tempted. The slope is not 1, because the scale of the y-axis is 10. So actually, the slope of this graph is up 10 over 1. Up 10 over 1. Up 10 over 1. So, for part A, S prime of 1 is up 10 over 1. Up 10 over 1 would be positive 10. And then what we have to say is, interpreting derivatives is really specific. So watch my language here. We have to say, at t equals 1, at t equals 1, the rate, now here's what we got to think, right? S of t already is a rate. S of t is the rate at which boxes of popcorn are sold. S of t is a rate. So we're measuring the rate of change of a rate of change. And we found out that the rate of change of that rate of change is positive 10. So I'm going to say at t equals 1, the rate at which popcorn is sold is increasing. Because S is the rate at which popcorn is sold. We just found its derivative. So the S, the rate at which popcorn is sold, is increasing because it's the derivative and it's positive. The rate at which popcorn is sold is increasing at a rate of 10 boxes per minute squared, or per minute. All right. Now, just as a quick note, just to help you out with the last parts, B and C, you definitely got to remember, just read the questions carefully. B, find the total number of boxes of popcorn sold during the first 10 minutes of the intermission. Show the computations. Measuring boxes sold, that means we need to do our calculation using S of T, because it's the only thing that measures boxes sold. We also, in C, want to do a midpoint Riemann sum. So you have to do the work with B there. In C, we want a midpoint Riemann sum with 3 subintervals to indicate the box is made. So that means the interval from 0 to 10, because all we're interested in is the box is made, right? You'll have to do the work there. What makes this tricky is we want 3 subintervals going from 0 to 10. So we have to chop it up into 3 subintervals. Subintervals are going to be right there. careful, the intervals are also slightly different, right? 2, 4, and then 4 again. So you'll see that on the answer rubric, but we do need a midpoint Riemann sum, not including this last column there, because we're only going from 0 to 10. 0 to 10 is all we care about there. You can check the answer key on that one. Do keep in mind for B, SFT is the absolute value, so you're going to need positives there. And then on the last page, just a quick note to maybe help guide you a little bit. Part D, write an integral expression for P of T, the number of boxes of popcorn available. This is our big equation, the one that involves both the initial amount plus the integral of the rate in minus the integral of the rate out. For E, this is another sort of theorem question. If it helps, go ahead and graph, because we're interested in whether or not the rate that the boxes are being sold is equal. If it helps, you can come over here onto your graph. G of T, remember, is the rate at which the absolute value of G of T is the rate at which boxes are sold. So G of T, if I could resketch that absolute value thing, something like that. Forgive the non-straight lines. We want to know, is there a time when the rate at which boxes are being made is equal to the rate at which boxes are being sold? These are both rate things. We can actually just plot our rates that are being made on this graph if that helps to visualize. 0 and 7.5. It's going to be just a rough estimate. 1 to 21, 2 to 27.5 or something. 4 to 34 is what, 32. 6 is 45. Right? And so if we think about the fact that, excuse me, we know that they're both continuous, so our F graph is going to do something like this. Does there have to be a time when the rates are going to be equal? Yeah, there's got to be some time in here. And then we can use the IVT to explain that, and that's what you see in the work. That there has to be a time. I just started to graph over here the rates that are being made. My graph that already was here was the rates at which they're being sold. Absolute value over here. There is a time where they're going to intersect. So you would have to show basically that these times cross. Essentially, you have to show that you go from 27.5 to 32. And then somewhere between 2 and 4, you go from 50 to 30, and so we have to cross values there. If you have questions about that one, let me know, and I can talk about it with you one-on-one. I hope you had a great weekend. Please check your work. You only have to fill out the score report form for that AB question, but you do need to send me your corrections and your work for everything. All right, take care, everybody. Bye.